We stand on the brink of a data revolution. Traditional storage methods strain to keep pace. But within our cells lies a molecule, elegant in its simplicity, powerful in its capacity to store information: DNA. Deoxyribonucleic acid, the blueprint of life, holds the key to unlocking unprecedented data storage capabilities. Imagine a future where libraries of information, entire archives, are housed within a microscopic strand of DNA. This is no longer science fiction. It is the future of data storage. DNA has stored life's blueprint for billions of years, an evolutionary marvel we are only beginning to harness. DNA's dense information storage capacity dwarfs even our most advanced storage solutions. A single gram of DNA can theoretically hold up to 215 petabytes of data, equivalent to millions of gigabytes. Imagine the 4 bases of DNA: adenine, A, guanine, G, cytosine, C, and thymine, T, as a 4-letter alphabet. Just as we arrange letters to form words and sentences, scientists can arrange these bases in specific sequences to represent digital data. This concept rests on a simple principle: translating the binary code of computers, 0S and 1S, into the 4-letter alphabet of DNA. Scientists achieve this by assigning digital 0S and 1S to specific combinations of DNA bases. This translation allows us to encode any digital information, from text and images to music and videos, into the language of DNA. DNA's remarkable stability and longevity make it an ideal storage medium. Unlike our current storage devices, prone to degradation and obsolescence, DNA can last for thousands of years under the right conditions. Imagine retrieving information from a woolly mammoth's DNA, unlocking secrets frozen in time for millennia. DNA's incredible density allows for compact storage solutions. While our current data centers consume vast amounts of energy and space, a DNA-based storage system could potentially house the entirety of human knowledge in a space the size of a sugar cube. Scientists synthesize custom-designed DNA strands that carry the desired information sequence. This synthesized DNA, containing the encoded data, can then be stored, transported, and even replicated like any other DNA molecule. Scientists use a process called DNA sequencing to read the encoded information. The decoded sequence is then converted back to its original binary form, making the information accessible to computers and other devices. Imagine converting a digital photograph into a string of DNA. The process begins by translating the image's binary code, 0S and 1S, into the 4-letter DNA alphabet, ATCG, following a predetermined conversion table. Each pixel of the image, represented by its binary code, is assigned a specific DNA sequence. These sequences are then chemically synthesized into short DNA strands, creating a miniature library of DNA fragments, each holding a piece of the image's code. To reconstruct the image, scientists sequence the DNA fragments, determining the precise order of bases in each strand. This sequence information is then converted back to binary code, effectively recreating the original digital representation of the photograph. The density of information storage is astounding, with the potential to store vast amounts of data in a minuscule volume. Retrieving data from DNA involves a process called DNA sequencing, a technology that has advanced rapidly in recent years. Scientists use sophisticated machines that can identify the precise order of the 4 bases A, T, C, and G in a DNA strand. This sequence information, representing the encoded data, is then translated back into digital format using the predetermined conversion table. The advancements in DNA sequencing technology have been crucial in making DNA data storage a viable option. The cost of sequencing has plummeted in recent years, making it increasingly affordable and accessible for research and development. The field of DNA data storage is rapidly evolving, with new breakthroughs and applications emerging at a breathtaking pace. Researchers are constantly striving to improve the speed, efficiency, and affordability of DNA data storage and retrieval. One exciting area of research focuses on developing more efficient encoding and decoding algorithms, optimizing the translation process between digital data and DNA sequences. Imagine portable DNA sequences capable of reading vast amounts of information stored within a tiny DNA sample, making information retrieval as easy as scanning a barcode. In healthcare, DNA data storage could revolutionize medical record keeping, enabling secure and efficient storage of patient data over a lifetime. Archaeologists could use DNA data storage to preserve fragile ancient texts and artifacts, ensuring their survival for future generations. The future of data storage lies in reimagining our relationship with information. DNA data storage offers a glimpse into a future where information is no longer confined to bulky servers and fragile devices, but intricately woven into the very essence of life itself. This paradigm shift in data storage has the potential to revolutionize various industries. In entertainment, imagine streaming movies and music not from the cloud, but from DNA molecules, offering unparalleled storage capacity and data transfer speeds. In education, imagine textbooks and libraries encoded in DNA, providing students with access to a vast repository of knowledge in a microscopic package. The ethical and societal implications of DNA data storage are vast and require careful consideration. Issues of data security, privacy, and access need to be addressed to ensure responsible development and deployment of this technology. The journey into the world of DNA data storage has just begun.